Alright, this is a brief introductory lecture for how to tackle Hardy-Weinberg problems. A little bit of review for those who have had me in evolution. This will look very familiar. So, I help place this where we are in the course. Although we will be dealing with evolution because evolution in a way is a change in allele frequency over time. Population genetics is the study of the distribution of alleles in populations and the causes of allele frequency changes, how alleles are born, lost, and maintained in populations. So I want to go back to this, which should still be a little bit of review, but familiar to all of you. In diploid organisms, there's a male and a female. Even in plants, even if an individual is a hermaphrodite, they make pollen and ovules. So, if it's diploid, and you've got one locus and two alleles in a diploid organism. Okay, so you can use the Punnett square to understand the genotype of an individual zygote. And if both, there are going to be four combinations that are possible. If both the sperm and the egg come from parents who are heterozygous, you can get all four combinations. These little a, big A individuals, even if they get the big A or little a from a different parent, they have the same genotype. So we can take this to the scale of population. So instead of looking at one Punnett square, we can essentially have a Punnett square for a population and look at what the offspring are going to be. So here we come back to the land of frequencies. We're going to have frequencies of alleles and frequencies of genotypes. And one place where many students get confused is in not distinguishing between an allele and a genotype frequency. Okay, so if we use this play schema, we have 36 of 100 individuals here with the big A genotype. We get, because of the, we can get big A, little a in two different ways, and that's nearly half of the population. And little a is the smallest proportion of the population. So out of 100, we're only 16. Okay, so the allele frequencies. Big A is 0.6 of the population and little a is 0.4. Now, if this is not clear to you, as this should be reviewed coming into this course, please take some time to think about this. If you're stuck here, you're going to be stuck most of the rest of the semester. All right, so with this we can calculate. We use big A and little a, or P and Q, as terms sometimes. These are just arbitrary units. So if we have two alleles of the locus, A and S, in a population that's not an even number, we can calculate how many big A and little a genotypes and alleles we have. So I'd like you to go through now. I'm going to stop the recording for a moment and figure out how many A alleles there are and how many S alleles, and what the frequency of the three genotypes is. So I'm going to stop here, and please do this math yourself. You should pause the lecture. And here I'm going to continue. So, if this population is in Hardy-Weinberg equilibrium now, so I'm going to pull in the binomial expansion. Okay, so we're going to use p squared, 2pq, and q squared to calculate the frequency of the big A, of the A, the S, AS, and SS genotypes. Okay, so here I'm using F to indicate frequency and subscripts. So I'm calling it p squared. So what I'm using here, if this is the assumption of Hardy-Weinberg equilibrium, this assumes a binomial distribution where the homozygous individuals of one allele could be p squared, and of the other q squared, and the heterozygous individuals 2pq. So now this is something where we can calculate expected and predicted. So in this population, these are the actual values, and they're very close. So there is a way to test whether they're actually close enough. This involves doing a chi-squared test or a test very similar to it. With large samples like this, you would actually do a maximum likelihood test, which is slightly more accurate in large populations than the chi-squared distribution. And if it were very small, fewer than 50, you would do a Fisher's exact test, which is a slightly different probability distribution than the chi-squared test as well. But that is how you would test it. And we look to see if these predictions match. So if you do go through and do the test, you would see that this fake population that I've given is in Hardy-Weinberg equilibrium. Okay, so we use Hardy-Weinberg equilibrium as a starting point. So we want to see under what circumstances there's change over time. Okay, and there are a number of things that cause violations of Hardy-Weinberg equilibrium. And this is going to be what we focus on for the rest of the course. The population is not infinitely large. If it's a finite size, this is almost always the case, particularly in vertebrates. If there's no selective difference, if there's no mutation, if mating is random, and there's no migration. So we're going to spend the rest of the course examining these factors more closely. So this is worth remembering. Now, if a population is in Hardy-Weinberg equilibrium, the allele frequencies are not going to change from one generation to the next. And if it's in Hardy-Weinberg equilibrium, we can use the binomial expansion, p squared, 2pq, and q squared, to predict relationships. This is only if we're in Hardy-Weinberg equilibrium. Right, so I'd like you to think about this. And one thing I want you to think about is what dominant and recessive mean again. We often use big A and little a, but those are just arbitrary. Dominant and recessive do not indicate a difference in performance. So I'd like you to write out a definition of these and think about what it means for homozygous and heterozygous genotypes.